Swayam Prabha. Digital India. Educated India.
Before we end the discussion on finite difference methods, let us consider the case of non-uniform meshes. When we say non-uniform mesh, the spacing between adjacent nodes is not the same. As illustrated in this figure, you have, this is a case of one-dimensional grid where this is for example the x direction, and the nodes are located at these points here. This is the ith node, this is the I plus 1 node, I plus 2, I minus 1 and I minus 2 like this, and you can see that the spacing between these two is different from between these two and between these two like this. Although it is shown to be gradually increasing and almost by proportion like a geometric progression, it is not necessary that it should increase in a specific way, but we do use this kind of geometric progression of the grid spacing for example in regions of large gradients like in boundary layers and so on, but a grid with spacing which is changing is a non-uniform mesh. So for such a case we can define a delta x, but the delta x is not the same. So we can associate the delta x of node I, we can define it as delta xi as xi plus 1 minus xi. So delta xi here is this distance. Okay, you could also say that is the average of this from the midpoint of this to midpoint of this, but this is one definition, and with this definition you can go back to the earlier Taylor series expansions and then still write, for example u of x u at I plus 1 as u at I plus dou u by dou I at I times delta xi plus dou square u by dou x square times delta x I square and so on like that. And so when we are expanding u I plus 1 in terms of ui, then we get delta xi, and if we want to derive a central difference formula we also need u I minus 1. Okay. So when we expand this in terms of Taylor series, now u I minus 1 is given as ui minus delta x I minus 1, which is this distance, delta x I minus 1 is xi minus xi minus 1. So that is dou u by dou x at I times delta x I minus 1 plus dou square u by dou x square at I times delta x I minus 1 whole square by factorial 2 and so on. So you can do this kind of expansions. Now if you have uniform grid spacing, when you add this expansion and this expansion, this term will cancel out for the first derivative, okay, when we are deriving the central difference formula. But in this particular case, because delta xi is different from delta x I minus 1, they do not cancel out. So in order to derive a proper formula, we have to multiply 1 by the expansion of this by delta x I minus 1 and this by delta xi, and then do further algebra to cancel out those second derivative terms in order to derive a second order approximation. So there is more algebra, more manipulation that is required, but essentially the same principle applies that we had used for the derivation of the central difference formula, higher order accuracy, accurate formulas, and slightly more complicated formulas arise. For example, du by dx at I is now expressed in the simplest case, it is ui plus 1 minus 2 ui plus ui minus 1 by delta x square, but in this particular case it is ui plus 1 times delta x I minus 1 whole square minus ui minus 1 times delta x whole square. You can see that we had to multiply the expansion of this with delta x I minus 1 and multiply this by delta x I and then do further manipulations. That is how this is coming here, plus ui times delta x I minus 1 minus delta x I whole square divided by delta x I minus 1 times delta xi times delta xi plus 1 plus delta xi. And this whole thing is formally second order accurate with respect to delta xi. Okay. So, let us see whether it stands a simple test, which is that if delta xi minus 1 is equal to delta xi, then we should be recovering the earlier formula. So, in such a case, this is delta x square and this becomes 0. So, you have ui plus 1 minus ui minus 1 times delta x square divided by delta x. So, these two will cancel this out and then you have you will have 2 delta x. So, that gives us ui plus 1 minus ui minus 1 by 2 delta x, and that is a second order accurate formula. So, in that sense this tends to the simple formula for the case of equal delta x, but for unequal delta x you have to have more complicated formulas. So, this is, and it is pretty straightforward to derive a second order accurate formulas for the first derivative and second derivatives that we encounter in our typical fluid flow problems in terms of Navier-Stokes equations, energy balance equation and so on. And so, it is not very much more difficult to deal with non-uniform meshes, okay. But we would like to make a point that highly non-uniform and distorted meshes should be avoided where possible, because this expression here is formally second order accurate, but let us say that delta xi is much greater than delta xi minus 1, okay. So, in which case this term will be very small, so it is negligible, and this term will be very small, negligible, and it boils down to first order accurate formula, okay. So, although it is formally second order accurate, if you have large changes in delta x, then you could it could effectively function as if it is a first order accurate formula and not a second order accurate formula, which is why we would like to make sure that sudden changes in delta x are should be avoided, and we make use of a geometric progression typically with an expansion ratio of the order of between 0.7 and 1.4. 1 by 0.7 is about 0.4 or 1.4. So, it is of that kind of range that we can use, and we should also keep in mind a geometric progression builds up very fast. So, if you use a geometric progression with an expansion ratio of something like 1.4 for 50 grid points, then the delta x variation can be very large between the smallest and the largest. So, you need to really see whether you would like to have that kind of variation and accordingly adjust your geometric progression based on the number of grid points you want to put and the domain length and what should be the grid size in the center and what should be the grid size close to the wall where there may be gradients, and so we have to take care when we make the mesh, okay. So, non-uniform meshes are probably unavoidable. Up to second order accurate expressions, they do not pose real great difficulty. As you go to higher and higher order accurate, then the algebra becomes tougher and tougher, okay. So, and we would like to point out that sudden changes in grid spacing should be avoided where possible, okay. So, with this we have covered the finite difference approximations for derivatives, and we have also applied it to a couple of example problems, and we have also seen time discretization, and in this lecture we will do a tutorial problem, but not on the board but in the computer, and this will also be an assignment for you so that you can work out on your own. And the idea of this exercise is to see for ourselves why it is not a trivial thing to solve Navier-Stokes type of equations. We have seen that using finite difference approximations, it is possible to reduce a governing equation into an algebraic equation. In the case of explicit schemes, it is possible to march forward from grid point to grid point and get a solution. very easily. Okay, but is it as simple as that? That is what we are going to do in this example. So, the objective of this test is that we know that for a given partial differential equation, a number of discretizations are possible. Okay, now the question is that are all these discretizations equivalent? Obviously they are not, in terms of, because there are some with a higher order of accuracy and some with lower order of accuracy, but we also know that order of accuracy is something which is only vague, it is not something definite. We cannot say that this will have so much error, because what we mean by order of accuracy is the magnitude of the leading term of the truncated series. And we have also seen that most of the first order, second order schemes will neglect lots and lots of terms, and only the first few terms are taken into account. So, there is no guarantee that the series starts converging within the first few terms. So, for large grid spacing, definitely the order of accuracy is not a good reflection of the accuracy of the solution. So, what is small is something that depends on the solution, that depends on the problem, and where we are looking at within the problem and so on. So, we would like to keep those notions in the mind, but we cannot say okay, this particular simulation has this much of error because this is first order accurate and second order accurate. That first order, second order only gives us an indication of how rapidly the error would decrease by grid refinement in the limiting case of very small delta x, but it is not really applicable for coarse grids. Okay. So, with this particular thing, we would say that we have seen a number of discretizations possible for the same equation, and we would like to see whether all of them would give us nearly the same solution, or some schemes, some sets of combinations of approximations will give much better solution than some others. So, for this we take a very simple example, a case study, and the case study is that of a linear convection equation, which is given by dou u by dou t plus a dou u by dou x equal to 0. Now, this is one part of a simple advection diffusion equation or a scalar transport equation, and so this can be considered as the left hand side of a one dimensional, for example, momentum equation with which is linearized, in the sense that in this equation u is a variable and a is considered as a given constant. Okay. And this is a partial differential equation, first order partial differential equation, and we will see some initial conditions and boundary conditions for this. And once we have an equation like this, then we can readily put in number of discretizations. Okay. So, we are considering 3 discretizations which will enable us to make a solution, and then these discretizations are somewhat similar, but they are also different, and we would like to see whether all the 3 will give us the same solution. Okay. So, for this we have the first discretization is what we call as forward in time and backward in space, FTBS scheme. So, the derivative, time derivative is discretized as a forward in time. So, that is ui n plus 1 minus ui n divided by delta t, and the space derivative dou u by dou x is put in the form of backward difference. So, that is ui minus ui minus 1 divided by delta x equal to 0. So, you have ui n plus 1 minus ui n divided by delta t plus a ui minus 1 by delta x equal to 0, and that can be rearranged to give a straightforward expression like this, ui n plus 1 equal to ui n, which is coming from the time derivative, minus, we take this to the other side. So, we get minus here, and the sigma is what is known as a Courant number, after a famous mathematician who brought out the Courant number criterion for stability, and this is a times delta t, when we take this to the other side, it becomes delta t in the numerator divided by delta x, which is coming from this. So, minus sigma times u I n minus u I minus 1 n, and we see immediately that this is an explicit method, because on the left hand side we have the variable that we want to compute. On the right hand side, all the variables are appearing at the previous time level. Okay, this is an explicit method, and we can also see the ui and ui minus 1, which makes it backward in space, and ui n plus 1 and ui n will make it forward in time. So, in that sense, this is a very simple prescription, and from a given initial condition we can march forward in space and time with this. So, this is one possibility, and we know that we are making this as forward difference. So, it is first order accurate, and here also this is backward difference involving only 2 points. So, this is also first order accurate. So, we have this approximation here is first order accurate in time and space. So, that is what we have in FTBS. In FTCS, we have the same forward in time, because forward in time with explicit method will enable us to get a quick solution, and at this stage we do not we want to test with simple expressions. So, so you have the same ui n plus 1 minus ui n, but the space derivative is expressed in terms of central differences. So, you have this as ui plus 1 minus ui minus 1 by 2 delta x, and we also make it explicit. So, we get ui plus 1 minus ui minus 1, because there is a 2 delta x, you have 2 here, and the delta x is consumed by this Courant number sigma here. And the other possibility that we can consider many possibilities, but let us consider another thing in which instead of using a backward differencing, we use forward differencing even for space. So, this will be given as ui plus 1 minus ui divided by delta x. So, that will give us ui n plus 1 equal to ui n minus sigma ui plus 1 minus ui n. So, these two are the same, except that we are taking a difference between ui and ui minus 1 in backward spacing, and here it is ui plus 1 minus ui, forward differencing here. And both FTBS and FTFS are first order accurate in time and first order accurate in space, whereas FTCS is first order accurate in time and second order accurate in space. Okay. And if you look at the way the solution evolves, that is how for a given set of initial conditions, how the ui n plus 1 changes with time, okay, how the spatial variation changes with time, is governed entirely by, obviously by the initial condition and the Courant number here. And what is this Courant number? It is the velocity A, okay, linear convection A, we will come to that, and delta t by delta x. So, the delta t is the time step that we choose, and delta x is the time step, is a space increment that we would have chosen here. So, what we do is that we can do in any kind of programming platform, or even in Excel, or even by hand you can do this, and so we have to fix a value of delta x and we have to fix a value of delta t, okay, and we have to fix a value of a here. So, for the sake of getting a numerical solution, we put a to be 1 meter per second and delta x to be 0.01, and so we take a to be 1 meter per second and delta x is 0.1, and u of x 0, so that is the initial condition, is given as a spatial distribution, and the spatial distribution is a simple rectangular pulse where it is equal to 1 over the interval of 0.1 to 0.2 and 0 everywhere else. Okay. The true solution to this is this pulse would get transported in the positive x direction at a speed of 1 meter per second. So, you can actually verify that by substituting a solution like this, that is u of x t equal to u of x minus a t is a solution for this partial differential equation. Okay. So, that means that if you have an initial pulse like this is travelling in the x direction at a speed of 1 meter per second. So, after say 1 second it would have traversed 1 meter here, and after 1.5 seconds it would have traversed the center of this would have moved by 1.5 meters per second. Otherwise the shape would be the same. If you had initially a triangular pulse like this, it would remain triangular, here. So, what we would be looking from our solution from the 3 different cases is that is the shape being maintained, okay, and is the pulse moving at the speed that is expected, okay, which is 1 meter per second. So, that is what we are looking for, and we would like to see to what extent the 3 methods that we have put up, which do not seem to have any problem with in themselves, okay, those seem to be quite good and straightforward things, to what extent they would reproduce this expected behavior. Okay. So, this is the solution that we are getting from FTBS at a time of 0.1 seconds, and we have 3 different solutions here for 3 different Courant numbers. Okay. So, when we say 3 different Courant numbers here, Courant number is A is delta t by delta x, A is fixed as 1 meter per second, delta x is fixed as 0.01 meters. So, delta t is given by the Courant number. So, if you fix Courant number to be 1, delta t will be equal to 0.01. If you fix it to be 0.05, then the delta t will be 0.005, and for a Courant number of 0.25, the delta t will be even smaller, 0.0025. Okay. And what we have seen from our error analysis and accuracy and all that, if we decrease delta t, then we should be getting more accurate solution, because for a first order if you decrease delta t by a factor of 2, then error should decrease by a factor of 2 and so on. So, that is the kind of thing. So, we would expect a more and more accurate solution as we go from 1 to 0.5 to 0.25, because delta t is changing, delta t is decreasing, and the solution that is shown here is actually shown here. There are these small curves here which are more software glitches, because it is trying to fit some smooth line through this. Otherwise, the solution that we see in green has a pulse, okay, of 1, maximum of 1 here, and it spreads between 0.2 to 0.3 at the end of 0.1 seconds. You can see that as part of the initial guess, we gave the pulse to be 0.1 to 0.2, and in 0.1 seconds it would have moved by 0.1 meters. So, it would have gone from 0.1 to 0.2 to 0.2 to 0.3, and that is exactly what we are getting. We are getting it going from 0.2 to 0.3 with the same value here. So, we are getting very nearly the exact solution, and whatever small changes here are because of the software is trying to make these things. So, if you plot the individual values, you will see the exact solution being produced by this green line, but if we make it more accurate, okay, as per our definition of accuracy, by reducing the delta t by a factor of 2 here from here to here, then we see that the shape is no longer rectangular, okay, it is more like a diffuse kind of thing. This is what we would have in practical systems. This pulse will not remain like a square pulse, it will be diffusing in this direction, and if you make it even smaller time step, it should be more accurate, but we find that it is actually less accurate as compared to the better solutions here. We see that the peak value has decreased and it has spread more. Okay. So, in that sense it seems to be counterintuitive to the arguments that we made earlier, that the smaller the delta t, the more accurate the solution, and here we have a solution which is not working like that. Okay. Now, what will happen if we go to a Courant number which is greater than 1? So, we found that best solution is at 1, and if you increase it by a factor of 11%, so delta t is increased by about 10%, 11% here, and this is what we are getting. So, you can see those pulse of 1 going from 0.2 to 0.3. So, we have exact solution here, and then it is 0 like this, but slight increase in the delta t has given us a variation like this by the dotted line, and this is not like the square pulse that we expect, okay, and it is not confined to between 0.2 and 0.3, which is what we expect, which is what we are getting with sigma of 0.1. And if you increase it by another small amount, okay, from 1.111 to 1.125, you see the value, it is going to deeply negative and deeply positive, and this is not like the rectangular pulse that we are expecting, okay. So, what we see here is that we have a solution method, this FTBS solution scheme. It looks like it is wholly unreliable. It is giving correct results only for one value of sigma, only for one value of delta t for a given delta x. For other values, it is either giving a diffuse solution like what we are getting here, or an absurd solution. So, small increase greater than this is giving an absurd solution here, and actually decreasing the delta t so as to get better accuracy is not giving as good a solution as what we got with this value, okay. So, this is surprising. Now, you look at the other FTCS, we expect this to be more accurate than the FTBS scheme because this is second order accurate in space here, and here we are looking at again at the same time of 0.1 seconds, and again with 3 different values of Coulomb number of 1, 0.5 and 0.25 here, and we should be ideally getting a pulse between 0.2 and 0.3 with an amplitude of 1. So, we should be getting something like this, and what we are getting is totally different things. It is, for example, the peak value here is with 1 Coulomb number we are getting a maximum value somewhere here of the order of 7 and a minimum value somewhere here, and it is not like the square pulse that we should be expecting here, okay. And for even smaller kind of things also we are not getting anything like the rectangular pulse. So, what should have been giving a better solution because of its inherent second order accuracy is not actually giving us a good solution, okay, and all because we changed it from second order to first order to second order in space. Now, if you look at the third solution, FTFS solution, and this is at even shorter time 0.05 seconds. So, it should have moved only by 0.05, it should have been between centered between 0.15 and 0.25 here. So, it should have been a square pulse, and what we see here are amplitudes of the order of 400, it should have been 1, and again it does not matter what kind of Coulomb numbers we have here, in all the cases we are getting absurd solutions, okay. So, what is this telling us? It is telling us that there is definitely more to the solution than just substituting the finite difference approximations for the derivatives and putting together a scheme. And so, we see that different solutions ranging from exact to thoroughly unsatisfactory have been obtained for this simple linear equation, and what we are dealing with in actual Navier-Stokes equations are nonlinear equations and coupled equations. So, and behavior of the solution seems to depend on the choice of delta t and delta x, okay. So, this is bad because if it is something to do with the equations we can blame the modeler, okay, or the mathematician, but these delta t and delta x are the choices that we have to make in order to get a numerical solution, okay. So, now the blame is on us, we have to find the correct values of delta x and delta t in order to get a solution, and we see that sometimes it is coming okay very rarely, but most of the time it is not coming okay, even for the simplest case using approximations that have nothing apparently no problem with them. Okay. So, this is a situation that we have with the simple linear convection equation kind of thing, and this brings out the difficulty in getting a numerical solution if we take a very naive approach. And so, what we are going to do in the next module is we will do a proper analysis of the discretization that we obtain from these kind of differencing schemes, and then we see what are the conditions in which we can get a proper solution. So, we look at concepts like consistency, stability, convergence, boundedness, all these concepts that have been brought into play here in order to come out with a discretization scheme which we can confidently say that will give us an okay type of solution. If not the exact solution, at least we should be getting an approximate solution which would have some features of the real solution. Okay. So, that is what we are going to do in the second part of this third module.